Now we'll just build upon what we studied in the last class. Last class we saw a little bit about the sizing of the complex static circuits. Now we will see the delays in complex CMOS and static logic circuits. Okay. So now if you see here, yeah, I will cover the stick diagram in the next class. Okay, and also that issue which you had brought out about another about the full adder, right? A different topology. Those issues I'll cover in the next class. Okay. Now, if you see here, let me first define something known as logical effort. Okay. So, what is an logical effort? We have one last class before the midsem. Okay, we'll discuss about the exams then. Okay, I'll give you how to go about preparing for the exam. Okay, that is after next to next class. Okay, so if you see here, if I have to keep the delays of a NAND gate or a NOR gate, we saw that the sizing with respect to the inverter, this is an inverter where the sizing is in the ratio 1:2. So I have to do this kind of sizing. Now if you see here, now this will ensure that the currents available are same, right? Or you can say the delays are same, right? Also, if you see here, the net loading, the net increase in capacitance in this circuit, how much will it be? Here if you see the gate capacitance at A, it is 2 plus 1 here, whereas here it is 2 plus 2 plus 2, 4. So this has got an logical effort of 4/3. That means this is as compared to the inverter. Okay, that is what we say. So this NAND has got an logical effort of 4/3. That an inverter has got, if you see here, the net it is 2 plus 1 3 as compared to the. So I put this, this 3 is with respect to the inverter. Now here I say 2 and 2, they are right. It is 4. No, 4/3. So that means this has got an greater amount of capacitance, right? That is one way of looking at it, right? And if you see the NOR gate here, now this is to be sized like this, right? For the same delay or for the same current, then it will be like 1 1, right? And it is 4 plus 1 5 here. Similarly for B also it is 5, so it is 5/3. So the logical effort for an inverter, logical effort is G. It is 1 here, 4/3 here, or 5/3 here. Is it clear what is logical effort? Yeah, Devdutt, is it clear? Okay. So the other way of looking at it is, if I keep this 1 1 and if I these as same as that of inverter, I keep 1 1 2 2 here, and I keep here 1 1 and 2 2 here, then this will have an delay of 4/3 times greater delay than an inverter. This will have 5/3 times greater delay than that of an inverter. Okay, that is one way of looking at it, right? So there are two ways of it. One is this results in a net capacitance increase of 4/3. Okay, so that is G. If I keep the current levels same, here if I keep the right here, the net capacitance increase will be 5/3, right? Or if I have to keep the current levels same, if I have to keep the current levels same, then it will be 4/3 times the the delay will be 4/3 times more. Okay, so there are two ways. So this is known as logical effort, right? Now if you see in the previous class, we discussed this chain of inverters. There this was an output node capacitance, so we call this as C internal. Okay, this capacitance at this node, C intrinsic. Okay, C intrinsic means the capacitance which is because of this gate to drain, gate to drain to body, and again here gate to drain here. Okay, and this is okay. Okay, let me go back here. So you have a doubt no, to repeat this. See, if I see here now, to keep the same current levels, right? If you have to keep the same current levels in these circuits, so that if there is an output capacitance CL which is much larger than the intrinsic capacitance, in those case I have to keep the current level same to keep the delay same, right? So I am upsizing these transistors, right? So that the current, so if the net capacitance at these nodes have gone up by a factor of 4/3 with respect to the inverter. So that is known as the logical effort, right? Okay. Similar, but if I keep this as same, then the net delay, if I keep these transistors as unit inverter only, then the delay will go up by that factor. Okay, so you can look it either way, right? Is it okay? Okay. Now while coming here, so this is known as the intrinsic capacitance. Okay, C int. So C int is nothing but because of the capacitances at this node because of these transistors, right? So all these body to drain and body to gate, so these 4 transistors together, they are known as the C intrinsic. This C int which is shown in the textbook, and this is actually C interconnect. Interconnect means because of the wiring in the layout. When you do a layout, then this interconnect capacitance will come into play, and this is the load capacitance. And load capacitance is basically because of the output gates which you are connecting here. So that comes from CG. So if it is connecting only to one transistor, you will have CG, but if it is driving, depends on the size of this transistor and also the number of transistors which this is being connected to. Okay, so that becomes CG or C low. And then we saw this equation where it is 0.69 RC, a simple RC model to compute the delay. So TP was given as R equivalent into, right? Now we divided those two capacitances, the net capacitance, into two. One was C intrinsic and one C external. Now this C external is actually sum total of this interconnect capacitance as well as this CG. Okay, so this C in is purely because of this, or you can say C intrinsic is nothing but the no load capacitance, right? So when there is no load connected, then this will be the right, this entire thing will be the delay, right? And that delay we are calling it as TPO. So I have taken C int as right, I have taken C int out here, so this becomes C int divided by C external divided by C internal, and this has become the delay of an inverter when no load is connected. So this becomes an TPO, right? So now it becomes 1 plus C external by C internal, right? C external by C internal. Now we also saw that this is process independent. Okay, why is this process independent? Now for an inverter, if I try to reduce R equivalent by increasing the size of the capacitor by the transistors, the internal capacitance will increase by the same amount, right? So this will remain same. So this is known as the intrinsic delay. Okay, this is going to remain constant and irrespective of the sizing of the transistors. Okay, can you please repeat the last slide? G significance with, yeah, that I think we already explained it. So this delay, okay, will be there. That is the minimum delay, whatever you do, that is when C external is 0, so this becomes 0. So this will be the delay. So delay will start from here and it will keep increasing as you keep increasing C external, right? Then we also saw that this internal capacitance is actually a function of the gate capacitance, right? Now if I go back here, this capacitance is actually a function of the input capacitance. What is the input capacitance here? It is actually sum total of the gate capacitance here, not only one transistor. This is driving 2 transistors, so it is the sum total of these 2 gate capacitances which is coming in parallel. And practically it has been observed that, okay, so I can call this C internal as an gamma CG. It is a function of this, and generally gamma is 1. Okay, so if I put C int as gamma CG, so this will become gamma is here, CG here, right? And what is C external by CG? That is known as effective fan out. Okay, effective fan out means the fan out means the CG divided the output capacitance divided by the input capacitance. That is known as effective fan out, right? C external by CG. CG is the input capacitance. C external is the external capacitance, right? This is the input capacitance. So output capacitance divided by input capacitance is known as F, which is known as effective fan out. TP is known as the intrinsic delay. It is sizing independent, and it is dependent only on the process, right? Okay, C dB ignored. It is not ignored, right? This C int is actually, right, it is a sum total of all this, right? C dBp. It is sum total of all these things, right? We are saying it has been practically observed that this, the whatever is here is actually a function of CG, okay, and that is being given by this, okay, that proportionality factor is given by this gamma. Is it okay? Yeah. Okay, so now this was, now for an complex gate, C internal is gamma CG, yeah, then C int is no, so gamma like C dB, so gamma is a fitting parameter, right? So that is C d, so it is an for different process, right? Obviously you can't relate, but it is a fitting parameter. It is observed for, if you see my last class, it is said that for most of the process it is a function, it comes out to be almost equal, right? It is not exactly matching, but it is, right, it will CGD is much higher to, yeah, that will be there, it is much higher to, right, dB, right? So this is what this is an fitting parameter. Okay, now if you see for an complex gate, if you have an complex gate, right, now TPO, right, it gets this equation for delay gets changed by P plus GF into gamma, right? Now why is it getting changed, right? G, because, right, now you have an what is G? This is the like logical effort required, right? So that means if you have, if with respect to the inverter, this is likely to have 4/3 times greater delay, right? So now this TPO is the delay of an inverter. So if I take it inside, right, it will become TPF by gamma, right? But you have not catered for an instead of inverter, I am using a complex gate. So that is the reason I have brought in a factor of G also here, right? So is it understood why I have brought in G here, right? I have brought in, see, normally for an inverter it is TPO into F here, right? That is for an inverter. Now mind you, this TPO is not for an unit NAND gate, right? I am going to talk about P, right? Okay, this TPO remains intrinsic delay of an inverter, right? So I am, if I bring it here, it will become TPOF, right? Since this is because all the computations we are going to do with respect to inverter, that is the datum line. So I have kept it as a TPO, and that is the reason I have brought in an factor, okay, G. Okay, because this is going to increase the delay, so that is the logical effort which I have brought it as G here. Now here this F, now for the complex circuit, instead of calling it effective fan out, this is now C out by C in. Now I am calling it as electrical effort. So there is a change in nomenclature. This is known as electrical effort. This is known as the logical effort. Okay, so electrical effort and logical effort. Now what is P? Okay, now what is P is, let me now, if you see there is no, if there is no load, right, if there is no load, then TP should be TP0, right, if there is no, if P is equal to 1. Okay, but that is not the case. Okay, now what is happening is, when you have a complex gate, like say this case, right, you might have sized this for equal currents, but still, because there are a larger number of transistors here, and the interconnections will be larger, so there will be parasitics, there will be some larger parasitics in this circuit, and it has been observed that, right, so even if you have sized it, but still the delay for a 2 input delay, if one, this is the delay of an inverter, then it will be the delay of a NAND will be n input NAND will be n input NAND will NOR also will be n times greater. So you see, and for a multiplier it will be 2n, and for x NOR it will be here. So this has come from, right, from the layout issues, right. So it is again assuming that simple layout structure. If you do if you don't do layout properly, this can further go up, right. So if you do a proper layout, still the delay will be more, right, because an inverter, if you do a proper layout, it will take a small area. Now if you are making a NAND gate, but you have sized it, okay, to keep the current level same, but what about the layout, right, there will be more number of wires which will be required, and things like that, right, all the routing issues, gate connections and all, everywhere, like there will be wires between the gate, when you connect two gates with a metal, also all those issues. It has been observed that practically that there will be some that is why it is known as parasitic delay. Okay, so that is the reason this P has come in here. Is it okay with all of you?
Hello, sir.
Yeah, tell me.
As far as the parasitic, I have a problem with the second term.
Okay.
I mean the GF by gamma. Okay. So why is it G is multiplied? Because let's not consider the parasitics at this moment.
Okay.
So in that way, let's say TP0 into 1 plus GF by gamma, if parasitics are not present, right? So my question is, in that case, now we have done the sizing.
Okay.
So now if we have done the sizing, so currents are same as far as the inverter is concerned, right? Like just like the inverter, right? So there would not be any further delay. I mean, for 2 input NAND gate also, since we have sized it, the delay would be equivalent to an inverter, right? So why is this G term is coming at the delay part?
Okay, because say it is, if I have sized it and if I have kept the current levels, okay, the input which will be applied to this gate, okay, it will take larger time for the input to raise to that level, because now the capacitance is much higher by a factor of G, right? If you look at it that way, isn't it?
Yes.
Yeah, it will.
Yes.
It will affect the previous stage that way. Right. Anyway, okay. and because this TPO, okay, I can reduce this if I start amending this TPO as the gate delay of this particular NAND gate itself. So this I am taking as an inverter, a plain delay of an, this remains an intrinsic delay of an inverter, right? Is it okay? This G will definitely affect the previous stage, or you can call it that even the previous stage is coming up, but the input, it is taking that much more time for it to get reflected into its input. So I put a G here. Okay. Is it okay? So even if you size it, then still this issue will be there.
So what is the basic objective of sizing in that case? Like, is it to make the, I mean, as far as the inverter is concerned, do we tend to compare the propagation delay just like an inverter, or is it like it can be changing? Like, what is the purpose of sizing for that matter? The delay is changing?
No, if you have an CL, which is a much larger, right, than the intrinsic delay, then if you don't size it properly in that case, then the delay will increase. It will not be same as that of an inverter.
Okay.
Okay.
No, but I think I think what he wants to check is that what is a point of making a double width, right, of PMOS, right? I think this is because to maintain the symmetry, I guess.
Yeah, that is with respect to P and N. That is to keep the rise time and the fall time same.
No, I'm saying that
your question is
while doing the sizing, ultimately, effectively, for any whatever fan-in that complex gate might have, effectively we are doing a W towards the pull down and 2W towards the pull up.
Yeah.
So effectively the pull down network and pull up network are equivalent as far as the CMOS inverter is concerned.
Correct.
Basic CMOS inverter.
Correct.
So in that way, propagation delay should not change. But here we are seeing it is changing. So what am I missing here?
It loads the previous stage.
Okay,
right?
so
if both are
for that,
see this
for that thing,
basically
was CL is very high. Now
this
we
approach,
are considering this.
Let me clarify that. If I am looking at it in isolation, two gates, right, an inverter and a properly sized NAND, right, and if there is an CL, right, load which is connected, so the time taken to charge that CL and discharge that CL for an inverter as well as that that has to for by an inverter and this NAND gate will be same. Is it okay till here?
Yes, yes.
But now I am talking about a scenario where I have multiple gates, a inverter which is driving a NAND gate, right, and an inverter which is driving another inverter, right. So in the total path delay, where will be the greater delay? The inverter which is driving the NAND gate, right, it is going to see an increased capacitance, right, by a factor of G/3, right?
Yes.
So I have to cater for that. So I am not looking in isolation, right? But still I will keep an higher side because I have to keep individual gates as close as possible. Okay, but I will have to take care in the if I speak only of that NAND gate and with respect to and then isolation NAND gate and an inverter, the output delays will be same. But if I am talking about a few gates which are connected in series and inverter driving, and like for example, let me say we are talking about these kind of scenarios, right? So now this NAND is going to load this inverter more, right? Whereas this is not going to load this, right? Is it okay? So we are talking about these kind of scenarios. Okay, so I'll come to that. Okay. So that is why this gets this equation gets modified like this, right? Now this is the intrinsic delays which I said. Now for a chain of inverters, what we did was we took this CL, we did Cn, we kept this number of stages as a variable, right? We kept this we only took like we made an equation where an f geometrically we sized this, right, and then we did a derivative and made it to 0, and we saw that for f is equal to 4, right, that is the best option, and accordingly we kept f is equal to 4 and we decided the number of stages. Okay, but for an complex circuits we don't have we can't suppose like these circuits which is already there, so n is not a variable here. Okay, these are we have to just size these gates so that for optimum delay, so n is no more an variable in that case. Okay, for a complex this is what we did for a chain of inverters. And now what we are going to do is, right, we are going to the concept we learnt last time is equally applicable here also, right? Now here this is the sum total of all the delays out here. There we kept this particular thing constant, right? We did geometrical sizing and we kept that small f constant as 4, right? Here we are going to keep f into gi as constant. Okay, so that is represented as a small h, so fg. So if you see here, So we are going to F1 G1, F2 G2, we are going to keep this as an constant, right? So now if you see here, there is two more terms which come in, which is known as path effective fan out. Okay, so if you multiply Fn, F2, F2, Fn, you get CL divided by CG1. So in such circuits also you have an C in here and CL here, and the F is C. For individual circuits, there we kept F constant here, right? And here in the chain of inverters, here in this particular case, F will not be constant, but F into G will be constant, right? So now the logical effort G, the total, the path fan out will be product of all the CL it is CL divided by CG, and path logical effort will be G1, G2, G2 into Gn, right? So now we do, if you have to keep the path effort constant, we are going to keep this constant, right? So I take small h, that is small h is equal to root n divided by f into g, right? This n is also fixed, it is not a variable in our case, right? Now, so f is a term corresponding to a fan out. It should consider gamma. Yeah, so we are assuming here gamma is 1 for most of the case, otherwise gamma is going to remain a constant irrespective of what gates we are going to use. Okay, we also saw that gamma is close to 1, so we will not speak about gamma time being. Okay, so we are going to find out h by using this formula, right? So once h is known, right, then G is also known for each gate, then I can find out F1, F2, F2, F1. So that is the way I do the sizing. So it will be clear with a few examples now. Now I have an inverter which is driving an NAND gate, NOR gate, and again a NOT gate. So I have to do the sizing of A, B, C. Right. So what I do is I first find out F, right? This is the total fan out factor. So it is 5 and 1. So 5 divided by 1, I get 5. And what about the total G out here? It is 1. And for NAND it is 5 by 3, 3 input NAND. For 2 input NOR it is 5 by 3, and this is 1. So I get 25 by 9. So H is equal to FG. So I get 125 by 9, right? And there are 1, 2, 3, 4 states. So small h I get as 1.93, right? So here it now F into G is, right, h. So I get so accordingly I can compute an F1, F2, F3 and F4, and I can find out what is the size of ABC, right? Now how to compute ABC, I have not I have left it here. You want to refer this book, Digital Integrated Circuits by Rabe. It is given in a okay manner in this book, but I am going to explain you slightly simpler method in another example. You can use that method and complete this problem. This problem is left half, and see what is the result what I am going to explain you, and what is given in the book is same or not. It will be the same. Okay, so this is the way we compute F1, F2, F3 and F4. Is it okay? Okay, till here. Let's take one more example. It will be still be clear. Now let's take, we didn't take a case of branching here, right? So this signal was going from here to here to here to here, right? Now this was feeding only one, this was only feeding one, this was only feeding one. Oh, okay, there were other inputs, but in my path none of my required path was branching out. Here now if I see here, my required path is branching out here, right? So let's, if I say G, right, and this is an inverter, this is an inverter. So G1 into G2 both are inverters. So for an inverter, G1 and G2 are 1 1, so I get 1. Fan out is here 90, right, and this is 5, so 90 divided by 5 I get 18. G into F I get right 18, right? So if I multiply this, now if I see the electrical load out here, right, for this it is 15 15, right? So 30 by 5 I get 6. And what about here? It is 90 divided by 15, 6. right? Now if I try to compute H, G1, G2, F1, F2, right, I get this 6, this 6, F1, F2, 6 into 6, 30, yeah, 6 into 6 I get 36, and G1, G2 is 1, so I get 36, right? So if it is 36, but GF is got, I just initially when I computed GF, it is only 18, so it is 2 times the GF. Why there is an error now? That is because I didn't consider the branching. So there is a branching here. So here the branching factor is 2. So I have to multiply the branching factor also to get the H. Now, so the H formula for H gets modified as GBH. Is it okay? Yeah, let me repeat it once more. Like I have one inverter which is driving one more inverter, right? It is driving 2 inverters and I have 90, right? So now if I see the logical effort of this gate is 1, because this is an inverter logical effort is 1 straight away, we know that. So 1 into 1, right? So the G is 1. What about F? F in this particular case is 90 divided by 15, right? And for this 90 divided by 36. For this, if it is driving 2 gates, right? So it is 30 divided by 5, right? So C out by C in. 15 is C int. Yeah, this is C int is 15 here, right? So C int is 15. Here C internal is right, 5. C int is equivalent to C gate. That also we saw that. Okay. So it is 5 divided by 30 divided by 5, 6. So now if I compute H, G1, G2, F1, F2, if I use this formula, I'll get it as 36, right? So 6 into 6, it is, I am getting G1, G2 is 1, so 36. Like, whereas if I do just GF, I am getting 18. So there is an error. Now why is that error coming in? Because I have not catered for the branching here. So wherever there is a branching, I have to put the branching also here. So this my final expression gets modified as GBF, right? Okay, now let's take an last example here. Everything will be clear now, hopefully. Otherwise, we'll repeat it in the next class, right? Now I have to I have this is 8. The size is 8. Okay, X, Y, and 45. I have to do the sizing. So this is the critical path. So I'll generally do the sizing of the critical path, right? First. Okay, this can be done later on, but this is the most important. So I'll do the sizing, right? So now I find out an logical effort. This is a 4 by 3. This is 5 by 3 because this is a 3 input NAND gate. This is again 2 input NOR gate, 5 by 3. So I get 100 by 27, right? Electrical effort. Now it is like 45 divided by 8. Total electrical effort is given here, 45 divided by 8. Now branching, so here there is a branching 3, here there is a branching 2. So the branching is 3 into 2, it gets 6, right? Now the total path effort is GBF. So I multiply these 3, I get 125, right? Now to get the stage effort, that is individually small h, there are now 3, 1, 2, 3, right? So that is why cube root, I take cube root, I get 5. So that means that I get 5, right? Now if I see here total delay with respect to an inverter, if I compare it with the parasitic delay. What about the parasitic delay? This is a 2 input NAND gate, so 2. This is an 3 input, so 3. This is an 2 input, 2. So there is 7 parasitic delay. So the total delay with respect to an indicate for with respect to an inverter will be 3 into 5. Like 3 into 5 means there are 1, 2, 3. Okay, right? So each one is going to have an H factor of 5. That means 5 times the delay of an inverter, because this sizing is done, right? Geometrically 5. So this will be 5. So 5 into 3 plus parasitic 7. So 22. So this will be the delay will be 22 times that of an inverter, right? Okay, that is actually 4.5 times of fan out of 4. that means fan out of 4. Okay, what is fan out of 4? So generally we express it like this. So if you see fan out of 4, so this is one inverter which is driving 4 inverters. So if you see here, logical effort is here G because inverter to inverter. Electrical effort is 4 because 4 inverters are there, and there is a parasitic delay of 1. So total delay here is 5 here. So that is why I say when I am driving 4 inverters out here with one inverter, so the delay will be generally 5 inverter delay, right? So since in the previous case I got 22 and 5 is corresponding to fan out of 4, I can express it as 4.4 times the fan out of 4 also. This is just an expression, right? So didn't follow 3 into 5, right? 3 into 5 is because for each I compute H is equal to 5. That means from here to here the size is going to be 5 times. So the delay is going to be 5 times. Okay, and there are such 3 different stages. So that is why I put 3 here. Is it okay here? This? Yeah, okay. And coming to the parasitic delay, I told the parasitic delay we discussed right here. So because of the layout issues, an inverter will have one parasitic delay. N input NAND gate will have N input NOR gate will have N parasitic delays. Okay, that is inbuilt because of the layout issues and things like that. So if you have, we have now this is right, 2 input, so 2 delays here 3 input, so 3 parasitic delay, 2 parasitic delay, so that has come to 7, right? Now now I have come here, now I have found H to be 5, right? So for this stage, if I take, right, F is equal to right, a product of H and like G and H, right? So F is equal to 5 divided by G. So H is constant for each of the stages. Okay, so 5 divided by G here, right? So now if I have to find size Y here, right, it is of 45, right? 45, and I am going to find out small h is what? 45 divided by Y, right? That is the electrical effort, right? So if I do this, so I get the value of Y, right? 45. Is this thing clear to all of you? How did I get Y, right? If I go back here, let me go back here. Y, right? So Y is what? Small. The fan out is fan out electrical work into the logical effort. Electrical effort into the logical effort is small h, which is 5 we have found. So what is the electrical effort? It is 45 divided by Y, right? C out by C in. So 45 divided by Y, right, into gate logical effort is equal to 5. So that is what we have done it here. Is it okay? So 45 divided by input is Y, right? Y, right? Now 45 divided by Y into the gate effort is equal to 5. So if I have to find out Y, I have taken Y there, I have put 5 here. So I get Y equal to 15. Similarly, to find out X, is it clear, Doshi? No? Okay. Yeah, I find a few no's. So let me quickly. So what is H? Small h. Small h is F into G, right? Right? Small F into G. Small h, which is 5. This 5 we computed here, right? How this has been computed, that is known, right? You find G, you find B, you find F. You take square root of cube root here because there are n is equal to 3. Is H clear to all of you? First of all. Okay, now H is clear. Now I come here, right? H is 5, which is F into G, right? Right? So what is F? 5 divided by G, right? So 5 divided by G. Okay, now what is F? F is CL divided by C in. So C in is nothing but the size here, Y, right? So CL 45 divided by Y is equal to right? And f, if I substitute for f, 45 divided by y, right? So I take that y here, I get an h in the bottom, so that f has come here, g has remained here like this. Is it okay? How did I get this y, value of y? Yeah, Balamur. Okay. Now I compute an y. Similarly, I compute an x also, right? For all these stages, f into g is constant h, right? So and g is known. So I have to compute f. What is f? For this it is 45 divided by y. For here it is x, so it will be 45 divided by whatever is y divided by x, so and so forth. It will go like that, right? So you have to put that value of x also. This is already known. So I get y is equal to 15, and this I will get as 10. Now the last part out here is this total gate capacitance is coming. This is 15, but for an 2 input NOR, if I go back here, right, for an 2 input NOR, there is a logical effort slide. Okay, for a 2 input NOR, okay, for a NAND the ratio is 4:3, right? Here it is 5:3, right? These ratios for a NAND. So accordingly, right, if I know the total here as 15, now I can put this is 1:4, that is a 2 input NOR. Similarly, for a NAND, right, if I compute x is equal to 10 out here, right, and how to divide between n and 4, that depends on the sizing, right? So here if you see the size of these transistors, how it is to be equally decided here, right? And a 1:4. Here I find 1:4. Here it is the ratio is for a 2 input NAND it is same, for a 3 input it will change. So accordingly, so those sizes can be decided out here between P and N out here, right? Is it okay? This is a 2 input NAND. For a 2 input NAND, you will find it is same, right? 2 2. So that is why it is sorry. So I think we are running short of time. I think we just completed on. So that is why this sizing is okay. All the this is same, right? I think even I think we'll be logged out of the imparters, right, at 2:30, right? So this final aspect I will cover it in the next class also. Okay, doesn't matter, right? How to do this sizing. Okay, we'll call it off today, right? Otherwise, once if x and y are calculated, right, this ratio between P and N, okay, that can be decided on the thing which we have learned, right? We did the sizing, right? So to keep the rise time and the fall time. So according to that ratio, we can fix the size of the P and N, right? For each of these stages, H will be constant, right? And that we have found out to be 5, right? This is X, this is Y, this is fixed A. It is known, it is told initially in the statement, it is 8. Right? X and Y were not defined here. So X and Y were not defined. Now I have to find out an X and then Y, right? So what is X in this? If it is X, right, then F for this state will be Y divided by X, and for this F will be 45 divided by Y, right? So that is the reason, right? So that is how we do it, right? So okay, so I think we will I'll just touch upon this in the next class again once more. Okay, thanks a lot.